Alright, this video is going to be working through practice problem 20.2. This is on page 907 of your textbook. We're going to continue talking about our thermodynamics we've been looking at and look at predicting the standard entropy change for a reaction, that's delta S naught of reaction, and then calculating what that actually is using some data values from the appendix of the textbook. So we're going to do this for the combustion of propane. So we have C3H8 reacting with 5 moles. We're going to be careful about the states here. Reacting with 5 moles of oxygen. And this goes to produce 3 moles of carbon dioxide and 4 moles of water, and we're going to say that's liquid water. We're going to have to pay attention to the states here because when we go and look up these data values in the back of the book, there is a difference in the standard entropy for liquid water versus gas water, so we have to make sure we use the correct values. So for the first part, predicting the entropy change, we just need to look and see what we usually look for is the number of moles of gas on the left-hand side of the reaction versus the number of moles on the right. So here we have 1 mole of propane and 5 moles of oxygen, so we have 6 moles of gas on the reactant side, and on the product side we only have 3 moles of gas. We only make the 3 moles of CO2. This is liquid water, so it's important to make that distinction. So in this case we're going from 6 moles of gas down to 3 moles of gas. So we're decreasing the number of moles of gas, and remember the entropy goes in order from solid to liquid to gas. So gases have the most entropy, and liquids have lower than that, and solids are even lower than that. So we're decreasing the amount of entropy here because we're taking 6 moles of gas and taking 3 of those, and well, they ended up being in the liquid water, but we're really reducing the number of moles of gases. So there's less entropy because gases contain the most entropy, and we have less gas in the product side. So we can just go ahead and predict. Let's say that our prediction here is that delta S naught of reaction is going to decrease, so it's going to be less than 0. The change in the entropy is going to be negative. And again, that's just because we're reducing the number of moles of gas. Gases can distribute entropy or energy the most, so they have the highest entropy. If you remove some of those, then you are lowering the total entropy there. So if we want to actually go calculate it, what we need to do is use that the entropy change, standard entropy change for a reaction, is equal to, and this will look fairly similar, it's the sum of the molar coefficients times the standard entropy of the products minus the sum of the standard molar entropy times the entropy of the reactants. So let's just rewrite this equation again, or this reaction. We have C3H8 in the gas phase with 5 moles of oxygen, also in the gas phase, reacting with 3, or reacting to produce 2 moles or 3 moles of carbon dioxide and 4 moles of liquid water. And all you would do is on the exam, or I guess not standard exam format anymore, but what you would do is you'd either be provided with this data or you would have a table where you could go look it up. So I've already done some of that work for us. If we go look up in the back of the textbook, propane has a standard entropy of 269.9 joules per mole times Kelvin. So we got to be careful. All of our enthalpy values, delta H, those are all in kilojoules, but this is in joules per mole. It's a lot lower value. The standard entropy of oxygen is 205.0 joules per mole. And again, we have to be careful because the standard enthalpy of pure oxygen is 0. So the delta H of formation for oxygen is 0. We set that as a baseline and say that any element that naturally occurs in its pure state that has 0 enthalpy to make it. But it still contains entropy. Remember, the third law of thermodynamics states that anything above 0 K and not a pure perfect crystal is going to have some amount of entropy. Just continuing on here, carbon dioxide has 213.7 joules per mole Kelvin of entropy, and water in the liquid phase So all of these gases are up in the 200 range. Water should be lower than that, and it is. It's only 69.94 joules per mole Kelvin. So all we do is we plug these into the formula that we wrote above, delta S naught of reaction. We're going to start with the sum of the products times their molar coefficient. So we have 3 moles of carbon dioxide times its standard molar entropy of 213.7 joules per mole Kelvin, plus, so that's the sum part of this, plus 4 times, try and be consistent with my labels here, 4 times the standard entropy of water, which was 69.94. And so that's the product side. So now we're going to do the same thing for the reactants. So minus the reactants, we had 1 mole of the propane times its standard molar entropy of 269.9 joules per mole Kelvin, plus the 5 moles of oxygen at 205.0 joules per mole Kelvin. And so now simply all we're going to do is just crunch those numbers. You get delta S naught of reaction. The product side, the left-hand side here, is equal to 920.86 joules per mole Kelvin, minus the reactant side, which was 1294, so 1294.9 joules per mole Kelvin. And again, we can plug those into our calculator. We should get negative 374.04 joules per mole Kelvin. So again, the entropy, couple of checks here, the entropy, delta S naught, should have units of joules per mole Kelvin, and it does. So that all works out properly. And we look back at our prediction. This is definitely less than 0. It's negative 374, so this matches our prediction. So the combustion of propane, in the greater scope here, the combustion of propane is a reduction in entropy. And we said that the second law states that the entropy of the universe must increase for a spontaneous process. So let's just write a quick note. But combustion is spontaneous. And by that I mean it doesn't just like, there's not just propane molecules floating around that just randomly burst into flame. It means that once it's started, it will continue going until it runs out of reactants. So we still need that activation energy, but once started, continues until out of reactants. I can spell. So again, just kind of taking a broader approach to this and looking at it and thinking about this problem a little more carefully for what we're going to be talking about later on in this chapter, is again, with the second law of thermodynamics, we state that the entropy of the universe for a spontaneous process must be increasing. It must be greater than 0. So our entropy of the reaction here is less than 0. So remember, delta S of the universe is greater than 0, and delta S of the universe, let's rewrite that. Delta S of the universe is equal to the entropy of the reaction plus the entropy of the surroundings. So for this process to be spontaneous, and it is, this is greater than 0, but this is negative. So that means that the entropy of the surroundings has to be a much greater positive number. And again, if we go back and think about this, that the combustion reaction, any combustion reaction, has a negative enthalpy. It's exothermic, so delta H is negative. Remember that delta H, so let's actually rewrite that. Delta H is negative. And remember, delta H is simply, we kind of rewrite this equation we used earlier, it's just T delta S. So the entropy is related to the enthalpy. So if this is an exothermic reaction here, so delta H is negative, that means that the surroundings are gaining some heat. So we'd say that delta H reaction is negative, then delta S surroundings must be positive. So despite the fact that this reaction has a negative entropy of reaction, the surroundings are gaining entropy because the system is losing heat, or the reaction is losing heat to the surroundings. So the surroundings are gaining heat, they're increasing in temperature, so that is an increase in entropy. So even though this has a negative entropy of reaction, the entropy gained by the surroundings from this exothermic reaction is more than enough to make up for that negative entropy of reaction, and this process continues spontaneously. It just goes and goes and goes until you run out of propane. All right, that's all we wanted to talk about with that.